Okay, it's Mr. Zafiro back here. We're going to do some more chemistry. We're going to move into section 6.2 as we go through the different types of chemical reactions. They've been put into categories. We did synthesis and decomposition yesterday, and we're going to do three different types of categories today. I want to thank all the students who reached out to me for questions. I really appreciate that. Remind you the best way to do it is through the discussion thread that I created in D2L and on our course website, and that way everyone can see the questions. I did put in solutions to Chapter 6 now. That was an oversight on my part, but the solutions for Chapter 6 are now there. Thank you very much for Sohan for pointing that out to me. I greatly appreciate that. Okay, well today we're going to be doing combustion reactions and the two types of displacement reactions. So, combustion reaction. The whole idea here is that we're burning something in oxygen. So a combustion reaction, fancy way for saying burning, is a chemical reaction in which a compound or element rapidly combines with oxygen. Rapidly combine, it's going to burn. Sometimes it burns slowly, sometimes it burns quickly in an explosion, but it's a burn. So usually, as you know, when you've seen wood burn or fuel burn from a propane, maybe in a barbecue, what have you, or the Bunsen burner in a science class, you get heat and you get light. Now, one of the most common things that we as human beings burn are hydrocarbons, fuels, gasoline, propane, things like that. So a hydrocarbon, just like the word is in its naming of them, hydrocarbon, is a compound made of only carbon and hydrogen. Hydrocarbons usually have this formula right here. CX, that means the number of carbons can vary. HY, that means the number of hydrogen atoms can vary. So CXHY basically stands for all hydrocarbons, all fuels, fossil fuels is their source that we can burn. And the X and Y can be 2 or 3 or more, and off we go. So the simplest example of this is burning uh, methane. It's got one carbon, so it can't get much smaller than just having one carbon. But you have to remember carbon forms four bonds. Remember the valence ionic charging on carbon? That's why there's four hydrogen here. And we've drawn some of these in previous assignments, activities we've done in class. I think we created this particular molecule with the molecular model kit. So some of these compounds are fossil fuels such as methane and petroleum oil. Fossil fuels are hydrocarbons formed underground over millions of years from remaining of once living organisms. The general equation for the combustion reaction of hydrocarbon is the hydrocarbon, whatever it may be, so we're keeping it open here, X and Y, plus oxygen produces carbon dioxide and water. Always these two, along with the energy of the heat and the light, which we're not going to write down here because energy is not an actual piece of matter. So we're just writing the matter here. So it says we write CXHY in the general chemical equation because there are many different compounds made up of only carbon and hydrogen atoms. The products of a hydrocarbon combustion reaction are always, 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 all right, carbon dioxide and water. Carbon dioxide and water both being greenhouse gases, by the way. So here's an example right here, the simplest one. Methane, a gas, burns in oxygen, a gas. Remember, it's O2. It's one of those special diatomic molecules, elemental molecules. That's the way it exists here on our planet. And it has to produce. This is pretty easy because the products are always the same, carbon dioxide and water. And then you can go ahead and balance it. And we've all done lots of balancing throughout our time in class, sheet after sheet after sheet of balancing equations. Okay, the next type of reaction we want to talk about is called single displacement reaction in our textbooks. You'll see these also listed as single replacement. It's the same thing, just different way of naming it. All right. So in a single, keyword being single displacement reaction, an element reacts with an ionic compound. So if you ever want to help yourself identify a single displacement reaction, in the reactant side, is there an element reacting with an ionic compound? That's a pretty good clue that you're looking at a single displacement reaction. During the reaction, the element becomes part of the ionic compound. So the element that was by itself becomes part of a compound, while one of the elements in the ionic compounds becomes an element by itself. So there's a switching of places here. The elements that switch places may be either two elements or, excuse me, two metals or two nonmetals. That's your choice. In the first type, so this is key, the first type of this single displacement reaction, a metal atom trades place with a metallic ion in a compound. So the general equation for this is this following. Here is an ionic compound, AB. A is the metal, B is the nonmetal. It's going to react with another metal called C. What does the metal C do? It comes around and it boots out, kicks out, displaces, replaces the A. A, get out of here. You're a metal. I'm taking your place in this ionic compound. So now it's Cb plus A. The A metal, which was in a compound, now is all by itself as a metal element. It's been replaced by C metal in the compound. Okay, so that's what I wrote down here, where the metallic element A is replaced by another metal C. In this type, so in this type of single displacement reaction, the reactants will always be a compound and a metallic element, compound, metallic element, and the products will also always be a compound and a metallic element. Okay, compound, ionic compound, and a metallic element. Always. So these are clues that will help you identify if you ever see a reaction. Hey, there's an ionic compound reacting with a metal, and it produces another ionic compound and another metal. Must be single displacement. All right. So let's do a real life example here. We've got copper uh, 2 chloride. Copper 2 chloride. You would be able to make this formula here by using the crisscross rule. And it's going to react with aluminum. Now the copper 2 chloride is in a solution. Look, aqueous. And you're going to drop a piece of aluminum solid metal into that solution. You let the reaction occur, and the aluminum, boom, kicks out the copper. And now you've got aluminum in here, plus the copper. Now I'm noticing this here, and I'm noticing that there's an error here. I'm noticing there's an error here because the aluminum has a valence of 3 plus. The chlorine has a valence of 1 minus, so the formula should actually be AlCl3. So that is an error. Let's fix that right there. Nevertheless, the aluminum has kicked out the chlorine. Boom, you're out. And replaced it. Excuse me, the aluminum has kicked out the copper. I beg your pardon. Boom, out. Metal replaces metal. And now the copper that was in a solution is out. It's a solid. And the aluminum has combined with the chlorine to be part of a solution. And what we have here then is a chance to do some more balancing practice. And let you take a look at that and see if that's balanced. It should be. Okay, so we fixed a little error here. So let's wrap up the whole idea of single displacement, the first type. A metal boots out another non-metal, takes its place in the compound, the ionic compound. The metal, in this case copper, that was part of the ionic compound is now all by itself as an element. All right, now still with single displacement, there's a second kind of single displacement. All right, in this situation, a nonmetal in a compound is displaced by another nonmetal. So now it's the nonmetal getting booted out of the compound and replaced by another nonmetal. Here's a general equation for this. All right, AB, all right, the nonmetal B in the ionic compound is going to react with a nonmetal C, and look what the C does. Boom, kicks the B out. So now the nonmetal C is part of the ionic compound, and B, which used to be the nonmetal in the ionic compound, is out on its own as an element. All right, so where the nonmetallic element B is replaced by another nonmetal C. In this form of single displacement reaction, the reactants will always be a compound and a non-metallic element, and the products will always be a compound and a non-metallic element. This is a very good thing to key in on because it helps you identify if it's this type of single displacement reaction. So let's do a real life example here, okay? So we've got potassium iodide in a solution, potassium iodide in a solution, AQ. The formula here would be found by using the crisscross rule, plus bromine, a liquid. Bromine is Br2. It's one of those particular elements that exists as a diatomic molecular element, just one of the ones on our list. That's the way it's found in nature, just like O2 or H2. That's the way it's found. And look what's happened here. The bromine, boom, kick the iodine out, takes its place. This formula would be found by using the crisscross rule, and iodine has been booted out. Now, iodine is also one of those special diatomic molecular elements that exists as I2. It's never going to be found as just a single iodine atom. It doesn't exist like that. I'm going to remind you, you've got that list, H2, that's the way it's found, right? O2, N2, so hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, 1, 2, 3, 4, 5, 6, 7. There you go. They're the ones that are found like that. And then you could go forward, and I think you've all become quite skilled at balancing. Try to balance it and then check what we've got here is the solution. Next we have double displacement reaction. Now, I'm going to remind you, just like the last time, some textbooks, some folks call this a double replacement reaction. That's okay, it's just a different name, but you will see it every once in a while. Now, double displacement reaction is very similar to this. Let's say you go to a dance with your significant other and you're dancing and you see yourself dancing, having a good time, and then across the dance floor you see your BFF, your best friend, dancing with their significant other. And then all of a sudden you decide to switch dance partners. So now you're no longer dancing with your significant other, you're dancing with your best friend's significant other, all right? And your best friend is dancing with your significant other. So that's what this is. There's been a swap here. So let's get back to the chemistry. In a double displacement reaction, the positive or negative ions in two dissolved ionic compounds switch places. This is key. It's in a dissolved situation. All right. So the general chemical equation for double displacement reaction is AB reacts with CD to produce AD plus CB. So if you take a look at it, one way of looking at this is A and C have switched places. You can look at it like that. The C is now with the B, and therefore the A is with the D. They've switched. In a double displacement reaction, the reactants will always be compounds. Always. You start with two compounds and you end up with two different compounds. Therefore, a positive ion would only switch places with a positive ion, meaning the metal switches places with the metal. The two positive ions will never pair up to form a new compounds because their charges will repel one another. So what does that mean? It means you could never on this side here, on the product side, get a compound AC. They're both metals. They both want to give up electrons during a chemical reaction. Won't work. Okay? So that blocks that from happening. The two negative ions will never pair up to form a new compound for the same reason. Double displacement reactions may result in the formation of a precipitate. Not always, but sometimes you will get a precipitate form. We talked about this for a while now in our class, and it was in another video. So let's do an example here. Aqueous magnesium hydroxide, there it is. Aqueous dissolved in a solution. How would we get this formula, you may ask? Through the crisscross rule right there, okay? And it combines with aqueous silver nitrate right there. Aqueous silver nitrate. It's in a solution. How would we get this formula? Crisscross rule. So then what you have to do is take the silver and it's now going to be with the hydroxide. And then you would use the crisscross rule to come up with the appropriate formula. The magnesium is now going to be with the nitrate polyatomic ion. There it is, magnesium with the nitrate polyatomic ion. And you would use the crisscross rule to find the appropriate formula here. Now this new compound is dissolvable in water. It's soluble, aqueous, but this one is not solid here. Take a look at that, okay? So this is what we call the precipitate. Now, you're in grade 10 science. You haven't been studying chemistry all that much. I do not expect you to know which ones will be soluble, dissolvable in water, and therefore write aqueous, and which ones would be precipitate. No. You can study this later on with your chemistry teacher, probably Ms. WT, and there's whole theories behind this and tables that can be used to solve that. All right? So we've gone through the second set of reaction types, section 6.2 in your textbook. I've assigned some homework. The solutions are now up. I have put the chapter 6 solutions up. I have fixed my error. I apologize for that from yesterday. Do your homework, but first read the textbook. Read the textbook. I hope you watch this video. Then there's some also, I put up some other nifty videos you might want to watch to help you see this and understand it better. Then try your homework. If you have questions, please ask me. I've put up that discussion thread, and you can ask questions in there so everyone can see the questions. And remember, be patient with yourselves. Take time. Please reach out to your friends. I have not seen everybody sign in yet. I really wish that would happen. Try again, contact your friends, tell them Mr. Zafiro is active on this website, and we'll take it from there. Stay safe. We'll see you soon. Take care. Bye-bye.